Okay, so this problem here, VSI 9, it's about a flux of a two-dimensional vector field, right? And we didn't talk about this in lecture, but there's a section here about it near the back of the book here. So you define flux through a curve by this formula, right? Hang on a second. So we have this formula here that defines flux through a curve. So it's still you're still looking at the normal component of your vector field, right? Normal component of the vector field per unit length along the curve. So let's see here. Yeah. Well, so the dot product of F with N is what you're in. In other words, the component of this in that direction, and then times the length of each little piece along the curve. It's the same concept of flux. I just got a different formula for this context. Does that seem okay?
Yeah.
Okay. So the question is how to compute it, and this is it looks like a line integral. In fact, it looks like a vector line integral because, okay, well, it kind of looks like a scalar line integral, but then you realize you're doing dot product with a particular unit vector, and so you know this is an oriented integrand. So you're thinking vector line integral. The problem is the formulas that we have for vector line integrals require that to be the unit tangent vector, not the unit normal vector. Right? So in other words, we need to figure out, ideally it'd be nice if we could rewrite this in terms of a dot product of something with the tangent vector instead of the normal vector. So the trick, this is kind of a clever little trick. The trick on the way to do that is to realize that that this tangent vector we're interested in is just a counterclockwise rotation by 90 degrees of that normal vector. And so if I were to take the vector field and do the same thing to it, if I were to rotate the vector field 90 degrees counterclockwise, then this dot product is going to be exactly the same as that dot product. So I claim that, well, that dot product is equal to that dot product, and good news, the thing we're trying to compute then becomes exactly a vector line integral of the sort that we already have formulas for how to calculate. Right? So the big question then is, what is this F perp thing? And it's what you get when you take your original vector field and you can turn it counterclockwise by playing this usual game. If you switch the coordinates, you put a minus sign on one of them and make sure to put the minus on the right one. Draw some sample vectors and persuade yourself which one that is. And I claim it's this way. And so, well, now we have, again, a vector line integral. That's just f perp dot dx. F perp is this formula. Dx is x prime dt, and you can compute this by the usual methods. Right? So in particular, then, we're going to apply, let's see, what question are we doing here? I already forgot. 9? Yeah, okay. So our vector field is x comma negative y. Let's write this down. So f is x comma negative y. That's your p. That's your q. Right? And so I want to know, what is f perp. F perp is, well, our formula back here. Oops. F perp is negative q comma p. So negative q is y, comma p, let's see, p is x. So there's your F perp. And the flux we're trying to calculate, as per this this business here, that flux that we're trying to calculate is line integral of F perp dot x prime dt. And so this is the usual now. Let's see here. So y comma x dot, well, let's see, this is x prime, y prime, dt. All of this stuff is functions of t, as per the statement of the problem. Namely, we have to parameterize the curve. Unit circle oriented inward. Okay, now we've got to think carefully about this now. Hang on a second. So let me draw over here. Here's our picture. There's our unit circle. We want to compute flux going inward, and when we rotated our unit normal vector counterclockwise, that gave us our unit tangent vector going that way, and notice that that is oriented clockwise, not counterclockwise. So what you have to do now is you have to parameterize the curve clockwise. So you're going to parameterize by x equals cosine t, y equals negative sine t. That make sense? Yeah. So take that, plug into there, 0 to 2 pi, and calculation. Any questions about it? Anybody?
Could you parameterize x and y with cosine t and sine t, and instead set f?
Yeah, sure. I mean, so an alternative, if you want to parameterize the unit circle going, in some sense, the wrong direction, like clockwise instead of counterclockwise. Yeah, one thing, an alternative you could do, let me write this down. So alternative, you could have x equal cosine t, y equals sine t, and then have set your starting and ending values of t to go backwards. So in some sense, this is going the right way, but if you have it start at 0 and go to negative 2 pi, t is going backwards, which effectively causes you to go backwards through the curve.
Actually, what I meant was set f perpendicular to the negative on what you have.
Set f perpendicular. I didn't follow. Say again.
So set f perpendicular to negative y, negative x. So let it actually point toward going inward.
Oh, well, sure. I mean, it's another way of introducing a minus sign. I mean, another thing you could do, by the way, is instead of parameterizing this thing backwards, you could just say parameterize it the normal way and just put a minus sign out front, because you're just parameterizing backwards, and so you're just all that does is contribute a minus sign to your final answer. And then so doing negative y, negative x, yeah, that's effectively taking your f perp and pointing it the opposite direction, which is just another way of introducing a minus sign. So sure, yeah, that'd be a fine way to do it. Any of those would be fine. Yeah. Anybody else? The criticism I would make of what you said there is it'd be a little bit harder to follow, like, why you did it. It's like, well, where the f perp seems inconsistent with what we've done in the book, and I'm not sure where this came from, and he parameterized the thing the wrong way. It almost kind of makes it look like you have canceling errors. So then it's not. I mean, your explanation is fine, but you would have to put the explanation in there so that so that the grader is aware that you didn't just kind of inadvertently have two canceling errors, which does happen sometimes. Yeah, right. Very good. Yes. Uh-huh.
Why the vector t goes out?
Why what?
Why the vector t?
Yeah. So the way when we wrote down that flux was computed by integral of f perp dot t ds, we defined t to be a counterclockwise rotation of your normal vector. Right. So our normal vector was given in the problem to be oriented inward. We were computing inward flux. So our normal vector is that way, and then a counterclockwise rotation by 90 degrees puts our t that way, which is clockwise, as it turns out. Yeah. Yep. Sure. Okay. Is everybody good on this one? Okay. All right.